the exam in the lecture. However, there was going to be a lot of references to this material, so I wanted to have this as a discussion so we can talk about it. You guys are going to be using motors. And I think as talking to one of the students, the student was saying, well, we're just told to hook it up and it'll make it go. So, it's like, I know we have a lot of people from several different departments or programs in this class now, so I want to go through that and actually bring us up to a common knowledge base. Because some of you have had some motor theory in some of your classes, so let's go ahead and talk about it. So we're going to talk about basics of DC motors. Okay, this is like starting with the simple stuff, and we're going to grow from there. We're going to get into stepper motors in the second module and talk about BLDC motors as well. So the slides have been uploaded. I also have a slide set on position sensors that do you want to have the discussion on today, or should we just meet with the team leads and have the sensor discussion next Wednesday? Next Wednesday for sensors? Okay. Because I don't know where you guys are at on your designs. I don't want to gate you and hold you up by not having enough discussion on them. So it's the slide deck for position sensors is about 27 slides. So it's not a short one. So these are both 19 and I think 15 slides. So there's quite a bit in this here. Again, it's informational. I'm not going to actually expect you guys to take notes per se unless you want to. The slides are posted in the lecture. They're in the lecture Canvas module so that everybody who has access, because I think there's one or two students who aren't in lab for this class. So let's talk about the basic DC motor theory. And we know from Lorenz's law that if I have a wire that is between north and south magnet poles, so I have a magnet here and I have a magnet here, and between these two magnets I've created a B field, right? And if I have a current through a wire in that B field, a force is generated on that wire. Right? That's Lorenz's law. If there's no current, then what happens? So let's suppose there is no current through that wire, and I move that wire. Then I induce a current, don't I? So it's a generator. On the other hand, if I have a current, then I have a force. And that force is orthogonal. There we go. We now understand what that means. My B field is in this direction, and my I is in this direction, then my force is orthogonal to the plane of those two. Make sense so far? So, what that allows us to do is we can be a little smarter about this. Instead of having a wire, just having a force, then what if we created a wire with a loop that we have here? Again, we have our B field. When we apply a current to this wired loop, then we get a force produced. Okay? So that's the application of Lorenz's law. That's what allows us to generate a torque from the current. And I say torque because we're dealing with a rotational force. So this is going to want to rotate about that axis, right? Is the word voltage anywhere on that slide? No. Does everybody see the word voltage? What is the electrical term we're using right here? Current. What is the mechanical term we're using? Torque. Torque and current are proportional based on this B field and the number of windings. So what that makes us realize is if I need to move a large force in a motor, that requires a large what electrical? Current. Not more voltage, more current. If this is being not allowed to move, for whatever reason, and I'm applying current, then what happens to the energy if the energy can't be dissipated through force? is generated by, or generates heat. Because energy can't be destroyed or created, right? Just transformed. So we're going to transform it. We're not going to use it as mechanical. It becomes thermal. In the power of that will be I squared R. I'm getting a little bit ahead of myself, and I don't have quite this in the slide, so that's why we're just going to kind of talk about more abstractly. So I squared R is the power dissipated in thermal if it can't be dissipated in a mechanical capacity. Right? Power into my motor equals power out. And if I can't exhibit the electrical power as a kinetic power, then it's going to be reduced to a thermal power. Everybody see that? Everybody agree with that? So if that's true, the thermal power has to be dissipated. Now, the wire in here to dissipate that energy shall be sufficient to not burn up, right? We've heard the expression, my motor's burned up. Is that reality? You guys you probably hear that colloquially, but is that a real expression? You guys tell me. Yes. Right? Because if my motor is exhibiting all of this energy, and it's trying to get rid of it, but it can't physically move because it's stalled or something's holding the end of that, and I'm applying power, but power is not going, so I'm applying voltage and I'm applying current, because that's power, electrical power, right? Or all I squared R is, once I have that voltage, I'm looking at this as I squared R capacity. And this energy has to go somewhere. It's going to go into heat. And if I can't absorb the heat in that winding, in that wire will break and melt. It will burn up. It turns into a resistor, it turns into a toaster element. Okay? Gets nice and red and goes poof. We burned up our motor. Literally, we burned up our windings. The point I'm trying to get here is this current's going to do something. It doesn't just stop if we don't stop, if we try to stop and prevent that load from being exhibited, or that torque from being exhibited. The energy is not going to stop for you. So we have to be aware of that torque-current relationship, because we might have the situation where we could burn our motor up if we can't make it move. And we're going to come back to that statement, but I want to kind of preface that. It's not in the slides, but I want to preface that with some context. Okay? All right, so here we are. Here's I cross B equals the F, right? So this is that little diagram we had right here. This is really what we're talking about here. So this is our force, but we're dealing with rotational force, so we're going to call it a torque, where that torque is really F cross L, right? So we have this moment arm where this force is applied, that becomes F cross L, but for time being, we're simply going to look at this as F, its own force. Everybody with me so far? Yeah? Anybody had this lecture before?
Yeah.
280?
I think so.
Sort of?
280.
Using some calculus.
The PLC class.
The PLC class? Okay. What's that?
I'm saying it looks like calculus.
Calculus?
Electric calculus.
Yeah, it's that too. It's also in physics. You guys get electrical physics, right? Yeah, so they talked about it. I'm totally glossed right over it. You really didn't have an appreciation for it yet. So now you do. Okay, so that's the same picture. So now let's look at actually how we build a basic DC motor. So we don't have square bar magnets and loops in midair. We actually have a cylindrical magnet right here. I stopped drawing these by hand because I actually took the time to draw by hand on this. I said, they look so good, I don't want to redraw them. Taking advantage of my hand drawings here. So we have these magnets, right? And I have a coil of wire inside of here, and I'm applying a current to my loop, creating a rotational force, i.e. a torque. To connect my source to my loop, I should have brought my little, darn it, I meant to bring that to them. So we'll walk out the door thinking I forgot something. I actually have a model of this motor that I built for my son almost, 10 years ago. He goes, Dad, how's the motor work? I don't know, let's go build one. So we went and we just built one. We literally built that little motor. I'll bring it for you guys on Monday. Sound good? But we have these brushes, and so we have basically a contact point, I have a bare wire that's connected to a bare wire. And the bare wire might actually have some other surfaces where it has maybe more of a round aspect of it that goes somehow connecting to this wire sticking out over here. So we call those the brushes. This is going to be known as a commutator, and we'll talk about what's going on with that commutator. But we're going to produce a rotation. So we need to get the current into that loop, but we have to have it so that this can freely spin, because this is not going to freely spin. So we need to have some kind of like a bearing surface, for lack of a better description. So think of that brush to the wire that we'll call the commutator. Think of that as like an electrical bearing surface, but it's also a mechanical bearing surface. And so to create this rotation, what happens is we're going to induce a current, or we're going to induce a force caused by the current through this wire. As this turns, this is positive, this is positive, this is negative. We're going to make this rotate, right? This is going to come around here, so it's going to disengage momentarily. So this is going to leave that brush. This brush that's over here is going to come around. I think I have that in the next slide. Yeah, here we go. So as we rotate around, this positive going this way now it becomes the negative. And the one that was here comes back over here and it becomes a positive. You may think of this in a way is we have a magnet in here and a magnet in here. So what we see is the plus here, as it's electrical, and this is the minus, this is a plus, it's going to repel and bring this over here. Hey, come to me, I'm opposite, right? And this comes around, and we create this inertia of this motor to start spinning through here. Everybody good on that? That's the physics of what's going on. So that's what we see right here. So we have this little rotation going on right here. I forget where I found the, I haven't made a GIF. GIF. What do you guys all say? GIF. I say GIF. I still say GIF. Because how do you spell graph? Oh, it's giraffe. Just saying. We call it a giraffe, not a GIF. It's a GIF.
No.
We don't say giraffe.
Well, gift has GIF in it. So like, I'm sorry.
It's a fun conversation.
I know it is.
So we have this animated GIF, or GIF, depending on where you're from. And we see, you can actually see the blue and the red as it comes around, and you see that that's actually going to rotate that. So that inner core, that loop, a single wire by itself isn't a very good magnet. So what do? We want to make it a better magnet. We can add more loops to it. But air is not a very good core for a magnet either. So we add metal. What kind of metal? Good magnetic metal, which would be a ferrous metal, tends to be what we call a soft iron core. And so that's what we have in the internals that loop is wrapped around to create a better magnetic circuit. I'm not going to go through magnetic circuits in this class. That's a different class I used to teach. But when I look at that, what's going on here, and this is kind of what we call the magnetic flux, as current is in this, as a charge travels in this wire and we have this current, we see that the field, this magnetic flux, is radiating outward from that center point. And so what we want to do is we want to improve that magnetic flux. And so what we do to improve that magnetic flux is we can, back before I'm getting ahead of myself on that one. What we see here is as we go through here, we see this is actually the direction of the magnetic flux that we see right here as it goes around in that loop. Or, I should say it this way. So it's going to go around, and we're going to see that the torque is generated right there. So the larger the current, the better the flux. But in addition, the more loops we're going to have, then the tighter that spacing is that we're going to have right here. Also, that a higher current, it takes a larger wire. Why? Because, and this is where I was prefacing that power dissipation problem. If I have a little wire, I can't have a lot of current through that wire, can I? Because why? It has a high resistance. I want to drop that resistance down as much as possible. So I want to drive a higher current, lower resistance. Otherwise, my power dissipated through that wire is only going to be I squared R capacity. If R goes up, it's not going to be very good. So what we want to see here is we want to have a big wire, ideally. But that's not always possible. But we have these limitations, and we have to worry about the power dissipation due to the I squared R loss of equaling power. So what can happen is if we need to move a force, a torque, let's suppose we have to move 2 Newton, 2 foot-pounds of torque. I don't care, pick your unit, it's Newton meters, pound feet. We have so much torque, but my motor can't deliver that. And I'm giving it current, I'm giving the power it's going to take. It says, hey, to get the current and the power, the I squared R, the VI, I need to get that motor to produce that amount of torque, or that amount of power for the torque, which would be the power, rotational power is torque times velocity, or omega. So it makes torque omega power equal IV, which becomes I squared R. Then that current, that wire size has to support that current, right? If I have too much torque applied to that motor load, and I'm giving it maximum current, or more so, then my motor will fail. Because my energy is now all thermal, and I can't dissipate that much because my wires are probably too small. So we need to size our motor. Bottom line of what I'm getting at is, when we stall, we have no rotation. We have no rotation, our energy is dissipated through thermal. We can't dissipate that thermal energy, it goes up in smoke. Question?
I was gonna ask, like, let's say like you have a motor like that, it's stalling. What if you just add like more turns on it? Does it improve the?
Yeah, you make a different motor.
You make a different motor,
But if you have a physical motor that you bought,
yeah,
and it's not rated for the load you're applying it to, it can't turn it. If you can't turn it, you're giving it all this electricity, all this power, right? All this V and all this I, what happens? It goes boom, right? We let the magic smoke out. So again, it can overheat and burn up a motor. So I knew I was going to talk about it, but I needed to give you guys a little bit more context because I'm jumping in a little bit on this slide deck. Okay, so as I said before, power into a motor is equal to power out. And power electrical in this case is IV or I squared R. It's the same thing. But mechanical power is PM. And so ideally we want to have a maximum electrical go to maximum mechanical. Now that's never going to happen. That conversion is never 100%. In fact, I think that's the next slide. So let's go ahead and look at that one. I'm never 100%. I'm going to have some form of an efficiency right here as I convert my electrical to my mechanical power. So this is my efficiency coefficient that I have right here. Ideally, P equals IV or I squared R equals torque omega, or T omega. But we know that that's never going to be 100% true. So this little model kind of shows this. So I've got the current, I've got this guy right here. I don't remember if I have this in that slide deck. Do I? Yeah, I do. Okay, good. Let me talk a little bit about that because I forget if I have this later on. When a motor is turning, let's think about what this motor is. The internal of this motor consists of what? I just showed you the picture. The magnets, right? What is that magnet composed of? Iron, and the big thing is the wire. Now, we said before, if my wire is turning in a field, what is being produced? If I physically turn that motor's turning in a field, in a B field, what am I generating? A current. So if I have a current and I have a resistance, what do I create? Voltage, right? I've induced a voltage by the very rotation of that motor. So that's what I'm showing right here. That's known as back EMF. Oh, that's what we're talking about in physics. This all in this back EMF. We're like, wait, how did I get there, right? Because this winding's turning. You made it turn, but it's now saying, hey, I'm a wire, I'm turning, I'm gonna induce my own current. Self-induction, right? It's not really self-induction because I've applied the power right here. But what is that going to do? The faster that turns, the faster that is being turned, what is being generated higher? The back EMF, right? So have you ever noticed when you plug in a motor, it starts to get faster, right? But does it, I mean, theoretically, it should continue on because if you know the Laplace transform of that motor, it's 1 over S, right? Which is an integrator. Which tells me if I apply voltage, theta should be incrementing and theta dot should be incrementing into infinity. But it doesn't. It stops. It gets to a steady state, doesn't it? So this guy right here is a governor or a throttling of the load because that back EMF is now going to get higher as I apply more voltage. We haven't talked about voltage yet. I'm just going to give you a little bit of a hint right now. The faster this spins, the more back EMF I've created, right? That's going to keep my motor from ever exceeding some maximum rotational velocity. It's a feedback system. So, again, going back to here, as the motor rotates, a given voltage across the coil is produced. We just talked about that. The rotation is going to change, induces the voltage VL, which is LdIdt. That's our voltage induction. Faster it turns, the more the voltage is induced. That's going to be known as back EMF. Oh! New for you guys?
Yeah.
Controls, we did talk about it, but not in gory detail with back EMF. I just said it's gonna be a feedback system. So let's look at this motor excitation voltage. I've got some V motor right here, and some of you guys, many of you should have, if not all of you, theoretically, if you had controls, should have seen this. But I know that that's not necessarily true. But this helped us develop the transfer function of a motor, if we recall. I'm not going to go into that level of detail. I'm just going to leave it, I think, where it goes this far. But what we have is, the V motor here is going to be the VR, the VL, and our back EMF. This is going to be our very simple first order differential equation. I can substitute and rearrange my torque equation. Like, what's that T coming from? Because I have power right here. And so torque omega equals IV, right? Or I is going to be torque omega over V. Right? That's just using that relationship. I'm going to assume 100% efficiency just because we're going to use it. And so that's what we see right here. So here's that torque. Current and torque go hand in hand. That's the one thing I'm trying to get across. But I can look at that some kind of coefficient with this term called KT, which is going to be my torque coefficient of my motor. Basically, that comes out of the efficiency between that motor power. So PE to PM. It's really going to be captured through this coefficient, oftentimes known as KT. Everybody with me so far? So we can think of KT as what creates that proportionality between I and T. Because we know they're proportional, right? Everybody agree? What's that proportion? I mean, we saw that before, right? At the very beginning. There was no voltage, it just had current and torque. Proportionality, really, we're coming from that B field for all intent and purposes. So far, so good? So that's the idea behind this expression that we have right here. So what are these implications? There's a maximum current draw when there's zero rotation. Maximum power is when there's zero rotation. When do I have maximum I'm gonna say this way. When do I have omega equals 0? Under what two conditions? Stall. Okay, that's the easy one, right? Too big of load attached to my motor. What's the other condition?
When there's like no current applied to it.
Not yet. Well, so if I buy a motor, it's not moving, is it?
Oh, there's not enough.
So I have a motor, and I'm going to apply it to a battery. Right? Just make it simple. Is it turning before I apply the motor to the battery? So it's at omega equals 0, right? So at stall, we already said it's at 0, omega 0. At start, it's at 0. Which means to make a motor go, you have to be able to give it enough current in order to make it start going. It has to overcome the stall start current, i.e. from the torque, maximum torque, for that. Now it's only a very short amount of time, infinitesimally small, but it's there nonetheless. So if you have a motor driver or some electronics, and we're trying to push that motor to start, and I don't have enough current being able to drive that motor, it won't go. Some of you guys noticed that in the controls lab. If your motor driver or the power supply was too weak, that motor won't start. Remember I told you guys, make sure if your motor is a 6 amp motor, your power supply shall be 6 amps or greater. Your driver shall be 6 amps or greater. Why? Because of that condition right there. That's our start condition. So we have start and stall. Stall, we're at that condition, we burn up our motor. But we have to have enough power into our motor from a current source to overcome that initial torque. That's really all these equations are saying right here. Now, here's the funny thing. So this is the basics of a DC motor. We just got done talking about it. Again, I could probably go into another 2 more lectures just on the theory of DC motor and magnetic flux. I'm not going to do that. That's a different one. Fair? Is that fair? Now, a stepper motor, it's interesting. So my maximum amount of torque is when omega is 0. Agreed? So we call that also a holding torque. If I can size my windings such that I can withstand that torque, that's good, right? If I can size my windings so they won't burn up, that's good. If I can design my magnetic circuit so that they don't burn up, that's good. So that I find when omega is 0, I have a maximum current draw. That's maximum torque. Agreed? So this is the idea behind the stepper motor. So here's our torque equation. It's going to be KT times V minus KT squared over R times the speed. Again, if that goes to 0, that's our maximum. And here's our power. If this is 0, then this is our maximum. Again, here's torque is proportional to current through some K variable here. And this is just kind of equating that value K to that torque rate. So if you ever look at the torque curves, that's how that gets generated. There's a good discussion in NICE's control book on motors. I did skip that in my controls class because I said just read it. It's not that hard. This is really, there's more discussion in that NICE book. Mechanicals, you probably haven't seen that. We're working on actually doing that in the new class for you guys. We are mechanical. You guys already. Okay. All right, so that's the first lecture. Yeah, so next lecture is steppers and BLDCs. So any questions on the basic theory of DC motors? Again, there's books just on this topic. One of the classes I used to teach went into almost 3 to 4 lectures on DC motors, on motors in general, AC, DC, synchros, etc. Any questions so far? Yes, sir.
So I guess when we were talking earlier about like stall, we were like how when you just start the motor up, that's when the current goes the highest. So I guess it's like it's a big consideration whether you do all the motors or not.
Great question. Absolutely. So if I have a power supply, then we saw a little bit that when we saw the robotics, right? They were struggling, weren't they? Because that power supply it's underrated. I have a new power supply I got coming in, so I'm gonna rebuild that power supply, redo that. So the power supplies are underrated, so they're great when you first buy them, then they kind of get really weak because you start drawing too much current out of them, they go, I can't do it anymore. They give up, they get tired. So now the new power supply, I'm gonna set up to that, it's like a 20 amp something or other. But yeah, you're right. Now, if I want to start one and start the other, then start the other, that's fine. But what if I need to hold that arm at a certain position in a servo position? I'm drawing maximum current. You even saw that robotics that did right here. The power supply would get basically give and you start to droop, didn't you? So I can't hold that current anymore. Just too much power. It starts to droop. Couldn't hold it. When to reset, because then the voltage is dropped. And then it goes into what's called brownout condition, causing the power supply, or causing the processors in that motor to reset. So you do need to have that. You can get away with doing that, but at the same time, you want to have that maximum current for maximum torque. The other thing we could do is acceleration. So this is going to get into things we're going to talk about in subsequent classes and subsequent lectures about a month and a half until we get to that lecture. But what does this mean? Do I apply a greater force or a greater torque requirement when I accelerate fast or slow? Slow, right? So if I have a less, if I want to move very quickly, right? So omega dot is not, omega dot is a big number. Omega is a big number, right? Power is a big number, right? Current, if voltage is held constant, becomes a big number, right? Power is power out. Which means if my current is insufficient, or if I want to move very quickly, my current isn't there to do it, I can't move very fast. But if I can control my acceleration, because as we talked about before, a motor does not instantly turn on at a given rate, does it? It accelerates to that rate. The rate of that acceleration, either commanded or inherent in the motor, is going to dictate what we're going to call an inrush current. But that's how fast that coil is going to absorb energy. But it's also looking at how that motor is going to speed up to a certain value. And if we can control that, make it go slower to get to that final value by controlling how that motor is being applied, so in other words, how fast we're having that motor spin up to a given rotational velocity omega, then I can reduce that current demand from my system. Everybody with me on that? So if I go too fast, I'm asking for a lot of current. The slower I ramp that up, the lower my current draw is going to be, my delta current, my I dot, for lack of a better description. Because my T dot and my I dot are proportional through some KT. Everybody with me on that? We're going to talk about that much later on when we talk about path profiles and why we might not want to just go 0 to 100%. Right? Why we might want to control that ramp rate of that omega. Okay? This is why. This is why. Not stepper motors, but DC motors in general. Everybody good on this so far? Okay. So the next thing, most of you probably aren't using it. Anybody using a DC motor for your design? Probably as a servo motor that you're buying the servo for, and you're letting the company makes a servo motor take that position and and holding torque and manage all of it for you, right? That's okay. Because that's what's going on inside of it. Servo motors are DC motors with feedback. That's all they are. So let's go to the next slide. Stats. And we're going to talk about stepper motors and BLDC motors. And so again, a little bit of review. So DC motors can be used as servo motors, providing servoing with position and or velocity. So we saw that in the RC servos many of you are using. To achieve that, we're using PI, PID, or PD, i.e. feedback control mechanizations, to achieve that desired position and or velocity. So motors are rarely used open loop. They are generally almost always closed loop systems. And again, controls, we did do that in detail. Now, suppose, again, we know that the maximum torque is when we're not moving. It's kind of counterintuitive, but it's true. And so the idea is, suppose instead of having a permanent magnet on the middle, and we put the we put a permanent magnet in the middle, and then the electromagnet on the outside. So we're going to flip the structure. And we want to take that inner core, and by energizing magnetic pairs, that core is going to follow the energizing of those outer magnet pairs. And when there's no energization, that's it. I'm making new words up. When the magnets aren't being energized to advance, omega is 0, right? If omega is 0, what's torque? It's maximum. So when my stepper motor is not moving, again, a stepper motor's idea is we flip the tube, and I'll show you some diagrams in here, but to kind of give you the heads up. As I drag that rotor around, when I'm not dragging it, I have maximum torque. When do I have a minimum torque? When it's moving, right? Alright, so a stepper motor, only the rotor is going to move. It's going to move in discrete steps based on the number of outer magnets versus the inner magnets. We're going to call those steps. We can do this in an open loop capacity. In fact, more often than not, we do this in an open loop. Steppers are open. Is it the best design? No. Is it a simple design? Sure. Does it get the job done? For most of your 3D printers, yes. High-end stuff, we may still use a DC motor, or that's a servo motor, or we might even use a servo stepper. But we're taking advantage of the fact that our maximum current is holding that torque. That's what we call our holding current or our holding torque. But again, if the torque requirement is too large, the motor can be damaged. Stepper motors can be what we call either polar, unipolar, or bipolar for how we energize the cores. I believe I have some of my diagrams for that. But if I look at a stepper motor, here's the basics behind the stepper motor. I think I have an animated GIF coming up. I can't remember. But here's the idea. So this is a full stepping of the stepper motor. We have our A and our A prime, our B and our B prime, C and C prime, and D prime. So like plus minus. Okay? But sometimes we'll reverse that minus plus. So it's not plus minus because as we rotate this guy around, this goes plus, then this goes plus, that goes plus, that goes plus, then that goes plus. Which means originally that's plus minus, plus minus, plus minus, plus minus, plus minus. So now the A that was plus becomes a minus. So that's why we don't call it plus minus, we call it A and A prime. Because these will flip halfway as that rotor goes around. You all see that? So that's all we're saying right here. So we're going to energize A, then B, then C, then D, and we're going to drag the rotor with us. So far, so good. That's the theory of the stepper. And so when we look at the stepper, the windings, there's a ratio of how many little notches are on this guy and how many magnets we have on this guy. So each one of these is a little magnet on this material. And that ratio is going to determine what's known as our step angle. So our step angle is 360 times the difference of the number of poles on our stator minus the number of poles on our rotor, divided by their problem. That's going to be the step angle or the number of steps that I'm going to have. So the number of steps per revolution becomes this right here. So this is my step angle or the number of steps that I have. So what that means is that's how far that stepper is going to advance every time one of these is energized. Typical step angles are 3.6, 1.8, or 0.9. Again, 360 divided by 10, right? Divided by 20, divided by 10. So that's kind of the idea that we see. So we look at these ratios, and there are some good ratios that work, but typically, most stepper motors, I think probably most of the ones you guys bought are probably 1.8s or 0.9s. Am I right? Yeah. Because it's going to be 360 divided by 10 divided by 100 is 3.6 divided by 200 is going to be 1.8 divided by 400 is going to be 0.9. Make sense? Of course. Okay, so again, NS is the number of teeth of the stator, and NR is the number of teeth for the rotor. Now, what if we want something better than that? What if we want something better than 1.8 degrees? So we said we were going to do a maximum voltage to turn this on to induce that current, right? Maximum, 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 maximum. But what if I got smart? What if I said, I want to kind of like drag it even in between those two guys. So I'm going to turn this one on and this one on at the same time. Turn on this one on mostly and this one on a little. So it's still going to point to this guy, right? But as I turn this one off more, turn this one on more, I'm going to be dragging it over here. So I can control how much I have between these two guys being on at once. Quite often, I can do that using a D to A to control that, and that D to A may be 8 bits. And so I might have a stepper motor that allows me to do micro stepping. By controlling that DAC with 8 bits, I can now do 1/256 steps between this one to this one. Now, if I do that, is my torque constant while in microstepping? William says no. The rest of you aren't awake yet. Is my torque the same at this spot or is a microstepping across? No, it's going to be lower, right? Because it's kind of like stuck between the two. So it's not 100% on this one. It's not 100% on that one. So it's not locked right in. So I do reduce my torque in there. So we're basically saying when we look at A is all of this. This is kind of like 1 minus that one. It's like the inverse of the two. That's kind of like the idea of what you see going on right here. We're supplying the inverse from the DAC. We can kind of think of this as A is kind of like the sine wave and B is like the cosine. In other words, they're 90 degrees out of phase. And that's another way that we might be doing that microstep. But we definitely have a lower current. If we have lower current, then we have a lower torque. Hence, we have a lower holding torque. Until we get to that cogged spot right there from B as we move to A, are we at maximum torque? Now we're at maximum torque. Reducing torque, maximum torque. We'll never get to 0 because we get to that halfway point and it can start kicking back into the other one. So we get to about halfway. It's not really halfway, but you get the idea, right? Because we're dealing with power. Power is really a squared function, so it's going to be 0.7 or so. Okay, everybody with me on that one? So here's some waveforms and some internals of a stepper motor. And I think, what? There it goes. Yeah. So you can kind of see it cogging around. If we have a unipolar, this motor that we see right here, it doesn't go to negative, it just simply goes positive. So it just re-energizes A, then B, then C, then D. A unipolar only goes A, then B, then C, then D, whereas a bipolar is that plus minus arrangement that I just got done talking about. Both are very popular. Unipolar is cheaper. Unipolar drivers are cheaper. Bipolar would be turning these guys on and opposite, unipolar just turns one on at a time. Has anybody ever tried turning a stepper motor? You can feel it cog, right? You feel it. That's the magnets lining up with it. In fact, if you want to take a motor and you want to figure out what coils are go to which coils, there's 4 wires typically out of a bipolar stepper motor. You have 4 wires. Take that one wire, try connecting it to each one of the other 3, and turn it. If you don't feel any resistance difference than when you don't have anything connected, those wires are not opposite to one another. But if you take one of you find it and you start turning, it's like it's really hard now, that's its opposite pair. Which one's A, which one's B, I really don't know. Maybe judge. But when you hook it up to a driver, if you don't know the motor itself, you see some motor off of some surplus motor, some stepper, I don't know what it is. You can tell if it's bipolar simply by doing that. If you don't have any changes, then it's unipolar. Make sense? It's an easy trick to do. Because again, understanding the structure of that stepper motor. And so we see inside these stepper motors, we can see how these coils are on the outside. And then we see that inner core in there as well, right? So that's that inner magnet. Now there are some, so you can see in here, the little teeth right here, and you can see the outer windings on the stepper motor. So again, the number of inner teeth here versus this guy here is going to be a 1.8 versus a 3.6, a 1.8, 0.9. You don't see much 0.45s. So you can see the unipolar. You can see the microstepping you have right here. A wave drive, I don't want to do that one. Half steps. What we're doing is we're kind of overlapping. So here there's no overlap, right? Here we're kind of doing the overlapping of each one that we see with each one of these phases. Here's a half step, and then here's that changing as we go up and down on a microstep. So far, so good. Again, this is a brief introduction on just the theory of stepper motors. I could spend probably 3 lectures on this also. I'm not going to. To make the move, you're probably just going to hook it up to a driver, right? Now, when I was a kid, we made our own drivers. No, we actually did. I made my own stepper drivers using some flip-flops to create the waveforms of when things turn on and off, driving it with a clock signal in a direction. It's a simple state machine. It's not that hard. It's a good exercise. If I teach digital logic, that usually shows up as a problem. And you know, but it's really not that hard, right? You're just going to create the waveforms from a clock. You're probably more accustomed to just sending in a clock and a direction of rotation, right? So what we're trying to do is, let's go back. We can go to this one. We're going to give it pulses, and those pulses are going to advance this rotor as it moves around, right? The faster we advance it, the faster it rotates. If we advance it too fast, and our motor can't keep up, what happens? We skip a step. Here's the thing. You can say, I'm going to give it 10 pulses at a certain rate, and therefore it's moved 10 steps. But if it misses a step, how do you know? You don't, right? Or maybe it's got a load and it can't extend that load, but it's turning anyway. It's trying to turn anyways. I.e., your printer when it didn't hit that home switch, right? And it goes, now you said you got to rehome it. That's always a problem. So closed loop stepper motors are better than open loop stepper motors. Open loop stepper motors are great when your load will not exceed the torque available. But if you do, then you have the chance of skipping steps, and you think you're one place and you're somewhere else. The only way you find out where you are is you go to some location until a condition occurs, i.e. home. Here I am, okay, now 0, 0, 0. You guys probably have done that on your printer or watch your printer. Everybody with me so far? So we know how a DC motor works in theory, the basics of it. We know how a stepper motor works in the basics of it. Again, if we want to have more lectures on this, I'll go deeper, but I think this is good enough to get you guys going. Is that fair? We can spend an entire class just on motors. I mean, an entire semester class. Okay. Which brings us to our next motor type, which is known as a BLDC. So think about a BLDC as if a DC motor and a stepper motor had a baby. That's about it, really. So our inner core of a BLDC looks like a stepper motor, although we could be brushing it through a commutator just to make things interesting. But we're going to drag that rotor along through the stators. However, a BLDC motor only has 3 windings on the outside. So each phase is 120 degrees apart as we rotate. And we control this. Think of this as microstepping. We're controlling these two until it's just this guy, until it's just this guy. So there's always this continuous phase of sinusoids that are moving along, turning on this one, then turning on this one, then turning on this one. As this one turns on, this one turns off. As this one turns off, this one turns on, so on and so on. But we don't do it as in a triangle like this. We do it in a sinusoidal nature. So we apply a sinusoid. We could do PWM, we turn it on and off. That's a simple way. If you're working on directs, that's what Ryan did. But you can do better theoretically. Okay, we can do a controller knowing if I can have some knowledge of where that rotor is. Stepper motors don't, but BLDCs can. If I can measure the amount of current that's fighting me as I'm coming through, or how much this is coming around, then I can use that voltage or that induced current to tell me where this guy is coming around. I can measure that. So if I'm looking at an ESC for my RC airplane and have a BLDC hooked up to my propeller, I might not have a sensor telling me where I'm at. I'm just simply measuring the drop in the applied induced voltage as this guy comes around. Because I have a back EMF on everything, just like we saw on a DC motor. So I can use that back EMF to know where this guy is rotating. As I know where he's rotating, because I only have 3 spots, I kind of want to jump ahead a little bit, right? I want to make sure I turn it on at the right time. So I can do that in a couple of different ways. I can use the back EMF, or I could use what's known as a Hall effect, where I have actual magnetic elements on the rotor, and it spins around. It's giving me a position of its position. They're relatively coarse. If I'm simply looking for velocities, that might be good enough. Or if I had a position sensor like an encoder, that's giving me a finer resolution of my current location in the rotation. That's to be very precise. Simple, okay. That's pretty easy to use, and it's pretty good. This requires a separate device, separate circuitry, separate software, but really, really accurate. All 3, super good. If you have this, you're probably not doing this, or you do this, you're probably not doing this. I've seen a lot of designs where we do both back EMF and the encoders. Just a little bit more information. Because this is continuous. This is discrete. This is discrete. And the problem with something that's discrete is it's only this or that. It's 1 of 2 possible states, right? I can't measure if I'm in between states. It's either on or it's off. But the back EMF, I can have a better quality one. Some Hall effects, I can actually look at proportional voltages as opposed to just on-off, depending on the Hall effect that I'm using. Okay. But encoders, they're digital, they're not subjected to the analog problems. So we see in here, here's our windings. Here you see the Hall effect sensors, and then there's the Hall effect sensors in here. So they bury the sensors into the motor inside, and it gets picked up outside. So this is what we look like in the waveform commutation to actually engage the BLDC motors. It's a bipolar, not unipolar. So that means things go plus to minus and minus to plus, much like we saw in the bipolar stepper motor. But we have to adhere to these one of 6 different phases. So we have A, B, C, and D, and we have the stators, or we have the states, and we can see this is like a positive, off, minus. And so we have 0, plus, minus. So here's plus, and it goes down, basically not used, it's idling, and then it goes to minus, and it's kind of like a free idle, and goes plus and free idle to minus. The timing of when we turn these things on and off is critical. This is what makes BLDC so hard. Because if we don't get this timing right off the bat, it won't work. It kind of coughs. Ask Ryan, he had that problem. So you got to know where you're at by reading the Hall effects at least, and the encoders would be better. So you know exactly where you're at, because when you start, you don't know that starting state. You just say, okay, I don't know what's going on. So in Brex, when we first started doing this a year ago, we were doing our own custom BLDC driver in software. And when you have a really simple motor or a very lightweight motor with not a lot of mass, it just kind of like moves to where it needs to go. But if I have a large motor with a large load, it's not going to just move. If I have a big gear train on it, it's not going to move. You have to move it where it needs to go first. And if you don't get the sequence right, it won't start. It just kind of jitters back and forth. So you have to get this timing on these states right here for each one of these sectors to sequence correctly. Again, by turning on plus or minus to each one of these guys as we move around. I think I have a video, I'm not sure. Yeah, here we go. And so here we see it from TI as it turns around, and we can see the different transistors turning on and off, or the different stators. So this is the switch that we saw right back here. So here are my 6 switches, and here are my 6 switches, and I'm turning on A, B, and C, and turning the plus and the minus as that center is rotating around. So I think this is pretty informative. You can see the induction caused by the initial inrush of the current that we see right here. So that's what we have with the flyback. So that's just it's restoring the current and coming and turning on immediately. And then we can see that flux in the waveform as well. So to do this, you would need in software several timers to create the waveforms that we saw right here for the on and off states. And if you really want to be good, you don't just simply turn on and off, but you actually control that voltage through here to some kind of an A to D and an amplifier. Those get real expensive, but they exist, but that's what you're paying for on really expensive BLDC drivers. There are some chips that actually do that for you. So some chips, the TI chip that we have allows us to make those adjustments if we want to, or if we just go simple mode. So we have field-oriented control drivers, which are known as FOC BLDC drivers, or FOC for field-oriented control. That's a very good control system. So let's think about feedback systems now. And I'm measuring current, and I'm adjusting that field of that winding field to drag that motor exactly where we want. That's FOC BLDC control. That's the pinnacle of BLDC drivers. For Brex, we're not there yet, but we want to get there here on Brex. That's a planned approach. Right now, we're just doing on-off trapezoid that you saw on that previous slide. Yes, sir.
I was going to ask if you go to the previous slide just to get a quick note.
What's that?
Can I go back to the previous slide to get a quick note?
Yeah. So we can do a full PID on each current into each winding. And you have 3 currents simultaneously being controlled. You have 3 PIDs simultaneously being controlled. You're controlling the voltages and currents into those windings for a given position based on what your feedback current is being measured at, as well as potentially an encoder. So you see where we're at. I mean, BLDC can get really complicated really fast. Even doing the simple stuff isn't simple. Can you do it? Yeah, I mean, if I had an FPGA, I've done an FPGA driver for this before. Not terribly hard. I mean, it's hard. But the timers, you need a lot of timers. So if you're using a microcontroller, you might run out of timers. So, yeah. A good friend of mine, Bobby, he also did one for them. He had to go one processor per motor, the full ARM 32-bit ARM processor per motor, using an M0. So that's the idea of what we have right here. 3 timers at a minimum for 3 phases. If you're smart, you might need 6 for various, depending on how you control the ISR. But we can do some analog PWM for smoother control, that phase control with FOCs. FPGAs are actually better than a microcontroller because you just instantiate one, you kind of have all 3, and then you can tie all 3 together. So it's very powerful. That's a really good senior project to an FPGA-based FOC BLDC. That's an alphabet soup if I've ever heard one. A BLDC FOC FPGA controller. That's a word salad alphabet soup all day long. But I mean, you know what it means. Or I could do an MC, same thing, yeah. All right. Anyway, but we could be doing PID or controls in general. We could do all 3 of them. So we could have a multi-input, multi-output controller or a MIMO controller for the FOC. I mean, again, acronym soup, I apologize. But you get the idea. And not only can we do the position, but we could also do velocity for each phase. We could even do acceleration control and limit the amount of current inrush that we have going into each one. So you can see these can get really big. If I have a really big BLDC motor that I need to really accurately control for some industrial process, that's the kind of control we need. Big robots that have big BLDC motors, not uncommon. That implies very sophisticated controllers, just in making the motor turn. We even talked about controlling the higher level loop of the position based on the feedback of that arm itself. This is just to make the motor turn. And when the motor turn reliably, when we say how fast and in what direction. So BLDCs versus steppers. No brushes, lower friction, significantly increased complexity for commutation. Versus BLDC versus DC versus steppers. DC has brushes, the others don't. But BLDCs and steppers are more complex. If I looked at complexity as easiest to most difficult, DC is the easiest for commutation. I did 2 little brushes, did a way of winding in a certain way, you're done. Steppers are a little bit more difficult. BLDCs are the most difficult. The BLDCs can support the highest current. It's really the highest power, most efficient motor. But the question I'm going to ask you is, if you don't need the complexity, don't use the complexity. If there's no reason for a BLDC other than the fact it's cool, that's the wrong reason. Okay? DC is just as good for most applications. Yes, I know most drills have BLDC motors now, with a little driver chip from TI, more than likely, or Infineon or a few of the other ones. But you're using a drill all the time, and you are kind of looking for efficiency on that. You're looking for durability, because if you've ever had a drill for a long time, you've had to replace the brushes. Not that that's a big deal, but, I mean, whatever. If you're dealing with something in an explosive environment, then yeah, the brushless can spark. As part of that can cause an ignition point. I don't know. If you're in that kind of an environment, you shouldn't be breathing the air. You shouldn't be there to begin with, personally. So, I mean, you know. But like I said, I go down by my new DeWalt drills, my new, all right, I have to ask the question. DeWalt or Milwaukee? Or McKee?
I'm a DeWalt person.
DeWalt? Anybody not care? Anybody understand the arguments on any of that?
I use
Whichever.
whichever.
They use whichever too. That's why I'm like,
Whichever won't work. I like yellow.
If you guys talk to any guys who are tool guys, whether they're contractors or engineers who use tools and build stuff all the time, you're going to have the thing. So if you want to start a flame war, there you go. So let's see. You have D10T with a stepper motor. You do not have D10T with the brushless DC or the DC motors, right? There's no cogging going on. So it's nice and fluid motion is what we're getting at. When we turn a stepper, we're going step, 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 step. So it's not 100% smooth. You hear this on your DC or on your printers, right? You hear the right? That's just the steppers going up and down in frequency, going faster and slower. You don't have that on a DC motor. You don't have that on the BLDC motor. Dave, you had a question.
I was just gonna ask, when I was working with a stepper, I noticed that every once in a while it started to jitter. Is that, I don't think that's what you're talking about, right? That's the-
That could be a variety of things with the driver going on. Yeah, that's just something's not commuting correctly. Yeah. Constant torque through rotation. Steppers do not have constant torque through rotation. A properly designed BLDC driver will and would at the same time. They will, as well as a DC motor has constant torque through full rotation. BLDCs and DCs are going to go fast. Okay? They are high omega motors. DC motors, if you've seen them with no gear, it's 10,000, it's 50,000 RPMs, right? There's no torque, so you got to torque that thing or gear that down. Almost every DC motor you have has a gear reduction. BLDC motors are about the same. If you ever look at the propeller on an airplane, or like the little RC airplanes, no gear reduction, that thing's just like flying. Literally, it's not flying, but it's spinning, right? It's going super fast. Stepper motors will not go that fast. They don't go fast. You have to commute and you have to get a bunch of mass going. But once you get those other ones going, the BLDCs and the DCs, boom, it's up to speed. It's going, it's carrying, it's on. So again, that's kind of a nutshell of BLDCs and DC motors. Probably didn't quite know. Some of you may have heard, don't use a BLDC unless you absolutely have to. Now you see why. It's not for the faint-hearted design. It's a full-on design just to get simple motors to go. Because that waveform, you got to control that waveform very precisely. Stepper motors are easier, for sure, but they have good carrying with it. If you try to use a stepper motor in a battery-oriented application, that's a bad idea. Why? Why is a stepper motor not good in a portable or battery application?
Because you have a constant,
If I'm not moving, what's going on? I'm in holding torque, right? And holding torque is the minimum or the maximum? Maximum. I'm drawing maximum power when I'm not moving. If I have a battery operation and thing's just sitting there, that battery's going, right?
Yeah.
That's not good. So stepper motors are usually bad for battery applications for those reasons. The DC servo motors, it's kind of a nice, so it's a DC motor with feedback in position, right? That's kind of a happy point between the two. Yes, you have a holding torque, but it's modulated as a function of the load demand based on the PID. So it's not always. You can servo a BLDC for position and or velocity, because at that point you're just controlling the motion. You don't care how that motion is generated. The BLDC driver is doing that for you. But commutation in a BLDC has to be done through some means of software. You're not doing it just through electrical. You can't do a simple state machine and flip-flops like I did back in the day. It's non-trivial. Steppers, you can get away with that. Yes, you can get smarter with microstepping, and those came out in the late 80s, early 90s. BLDCs really were a theory, not really being used and implemented throughout. Now we start to see those happening because we have really good drivers from, say, TI, ST, and those types of companies where they do the hard work inside the chip for you. They're doing FOCs if you want to do the FOCs. That's where you use them, but sometimes just getting those working are still not true. Questions? So I know a little bit to be dangerous about the three and why you might choose one versus the other. That's really the point of all of this. So as you're thinking about your designs, I think many of you are probably doing stepper motors, probably just like it's the right answer, you don't know why, but I think now you can justify that why, right? You can see where a stepper or where DC servo might be good and why you all want to maybe use the BLDC, said now is probably a bad idea, and now your gut was telling you why. Okay, so that's all we've got on motors. Next Wednesday, we will talk about positioning using potentiometers, encoders, synchros, and resolvers. That's it. The rest of you guys free to go. Leads, we're going to have a quick meeting, go over some of the rules, and if there's any questions. Other than that, I'll see you all in Butcher.